Alright, in this lesson we're going to be looking at the electromagnetic spectrum, and some of the things that we can get out of that are pictures we use our different time telescopes, and we can see different things as we look at space. So this is a picture from the Very Large Telescope Array that's in Chile's desert. So when they talk about the Very Large Telescope, they can either be talking about one really big telescope by itself, or they could be talking about an array of telescopes where they point it's kind of like pointing satellite dishes up at the sky and collecting radio waves from there. So they can be found in different ways. This particular one is one single telescope that they were pointing up into the sky, and what they saw was this planetary nebula. So if we remember from the life cycle of the star, we have in our low mass star, right, we have our protostar, and then it starts to fuse hydrogen into helium, which makes it an actual star. It's on the main sequence, and then as it loses its hydrogen and it's fused all its hydrogen into helium, and it starts fusing helium into carbon, the star expands into the red giant. And when it's fused all of its helium, remember now it's going to start to fuse carbon, and the temperature goes way down, and it can't support all of that. And eventually the gases just start to move away from the center, and what's left. Remember, we're going to end up left with a white dwarf in the middle of our planetary nebula. And so the big green bubble that's around it, those are all the gases that are moving out away from the remnant, which will be the white dwarf that will be left behind. So if you look in the picture, there's just one little bright white spot right there, and that's probably what's left of it. That'll be the white dwarf. And so eventually, over millions of years, we won't be able to see that gas cloud anymore. But remember that light takes a really long time to get to us. And so what we're seeing is a look back in time, because this all happened a really long time ago. So at the place where the white dwarf actually is right now, it doesn't look like this anymore. So it hasn't probably looked like that for a very long time. So, but still very cool. And it's something that we can find when we're using the electromagnetic spectrum and we're looking into space. So a spectrum is just that energy that's released. It's broken into wavelengths. And wavelengths are show us the speed or the frequency with which energy moves. And so the visible light portion of the spectrum is our Roy G. Biv, or our red, orange, yellow, green, blue, indigo, violet. And they go we learn them in that order because that's the order of the frequency of the wavelengths. So going from our very slow to our very fast. So the wavelength is the distance between the peaks, and the closer the peaks the wavelengths are, then the faster the wavelengths are moving. So red light here has the longest wavelength, which means it's moving the slowest. There's the least amount of energy that's packed in between and the amount of time it's moving. And our violet light over here has the fastest wavelengths, which means it's oscillating or it's moving the fastest, because those wavelengths are really, really close together. So if we see if I can do this, pen. So over here, our wavelengths, when we talk about our wavelengths, we're talking about the distance from here to here. Okay, that's one wavelength. So our red ones are going to be further apart like this, and our indigo or our violet ones are going to be much closer together. So our wave is oscillating or vibrating faster, and it makes a different color. That's not all the wavelengths there are out there. That's just a small little part of the spectrum that we can actually see. As we get even slower than our red, which is the slowest that our eyes can see, then we get into our infrared, okay, or our below the reds, our microwaves and our radio waves. So you've heard of these, like the radio waves. We're talking about the same kind of waves that come out of the radio. Okay, so if you turn on the radio in your car, or your parents' car, or wherever, those waves are moving at a very slow pattern, okay, and we can hear them, we can't see them. That's why we use them for music and things like that. Microwaves, what we use to cook our food with, right? So the waves are moving slower, which means that what they're doing as these wavelengths are moving through the food that's in your microwave, it's actually causing the molecules within your food to start to move at that frequency. And as they move, it causes friction, and that's why your food heats up. It's also why on most packages, when you look at your food, like if you look at something that's going to be microwaved, it tells you to let it sit, okay, before you eat it. Because what has to happen, what they want you to let happen is they want you to let the microwaves stop moving in the food, okay, before you consume it. Because if you consume it right directly out of the microwave, those microwaves are still moving in the food, right? And that causes the food to cook, and if you consume it, okay, now the microwaves are moving inside of your stomach, okay, or down your throat, and that's how it burns your throat, right? Because the waves are still moving through that, which cause the particles to oscillate, which is what causes the heat. So they're telling you to let the food sit so that you're not cooking your insides. Just a little side note. These kind of waves generally are not dangerous to us unless we get directly exposed to microwaves. Okay, like you stick your hand in the microwave and are somehow able to shut the door and actually expose yourself to it. Not very dangerous. The parts that I was talking about, it could be uncomfortable as you scorch the inside of your throat a little bit, but not really going to be hot enough to kill you or anything like that. As we get up into these faster moving rays, um, and waves, these are the ones that can be dangerous to us. These are the ones where the UV light, right, that's what our sunscreen blocks out, is UV light. That's what also our atmosphere filters out for us, which makes it very important to us. X-rays, if you go get x-rayed, like let's say you have to get some dental work done and you get your x-rays done, that's why the person who's doing the x-raying either goes into their own little room and has their little cubby, or they put like the lead vests on and they put the lead vest on you, so the x-rays are only going into the part of your body that they want to actually take the image of, because they're moving energy through your face, okay, especially if they're doing if you're doing dental work, they're moving it through there at a rapid pace. That's why they don't want to do it very often, because x-rays can be damaging if it happens all the time. And that's why the people who work there, who they would be exposed to x-rays all the time, that's why they usually have their own little place that they go to. Gamma rays obviously moving the fastest. Gamma rays are cancer causing, or can be. They can also be used on the flip side of that to kill cancer, which is why if you've ever been around anyone who's had to have cancer treatments and they had to have uh, not chemo, which is where they take something, like they take a chemical to kill the cancer, but if they're exposed to radiation, okay, what they're usually using are gamma rays. And once again, they'll do the same kind of thing. They'll actually have like a protective mask if it's on their face or on a part of their body, or a tube where they put the gamma rays down the tube towards the person's body so that they're targeting only the area that has the cancer. So they don't want to spread those gamma rays further through your body because they only want to kill the cancer cells. They don't want to kill your healthy cells. So our spectrum has a wide range of wavelengths, and so we can see parts of it. And then some of them, when we look at some of our images from further away, what we're seeing are false color images, and some of that is done based off of the radio waves and the x-rays, because when they look at that and they see the color that's coming back, they can tell you what elements are actually inside that star, and we know what color elements burn at, and so we know what color the star is. So even if we only can see it through x-rays, they can tell what the elements are, and then they can produce that kind of false color image in order to show you what color the star is. So we do this by spreading the light that comes out of the star into what's called a spectra. And you would have done this in elementary school with a prism. It's the same basic principle. You take a flashlight, you shine it on the prism, which is usually triangular shaped, and it breaks it into the rainbow, right? It's the same basic principle. When you use their flashlight, it has basically all colors of light in it, which is why it makes the Roy Bib, or it makes that rainbow that comes out of it. Stars, because they're burning particular elements, will only produce light that is reflective of those different elements. And so the spectroscope helps us to break that light into the different colors for those different elements. And so they can look a lot of different ways. They can also be attached to our larger telescopes. And so lots of different ways that we can see it. This obviously is a little bit more old-fashioned one. This is one that's um, not quite as high-tech. It's something that you can see in a classroom um, where students are learning how to use it. But what you're going to see when you look at the light is you're not going to actually see light come back at you. You're going to see a spectra. And so depending on what it is going to be either it's going to show a continuum where there's no break at all. That's if something's really, really hot um, and very dense, it's not going to have these black lines or the red lines or something like that in it. It's going to be all one thing. So if we get a hot gas that's very thin, not very dense, we'll see a lot of black and we'll only see the emission lines. And so we look at these emission lines and we match it up with what we already know exists by different elements, because we can burn those elements, we can look at them through the spectroscope, and we can see what the emission lines look like from a particular element as it burns. So then when we look at the star, we can see that if we see those same lines, then we know that that element is present. So when you look at it, if you look at sodium burning, okay, and you look at it through the spectroscope, all you're going to see is this one yellow line through the middle. And so when we look at our sample star here, if we see a line right through the middle, then we know that sodium exists in that star. So we can kind of match it up. So here's Mercury. You'll see how there's the two lines here, but there aren't two lines here. So Mercury's not in there. Doesn't matter if anything else matches up. See, these ones over here kind of look like they match up. They're pretty close, but not quite. But there's not these two lines over here, so we know that there's no Mercury in that particular star. We can sort of match up here. This one kind of matches up. This one does not at all. This one, so there's no lithium in our star. Okay, we have this one here that matches up right here. We have this one that matches up. We have this that matches up. These two are pretty close, which makes sense because our star currently is on the main sequence and it is fusing hydrogen into helium. And so we should see hydrogen in our star, because that's where it's at. So what you're going to be doing is an activity called Decoding the Cosmic Spectra. You're going to go onto the website that's on your handout, and you're going to be looking at, through an interactive, some different elements that are in a star, a planet, a galaxy, and the Orion Nebula, and you're going to be deciding what elements are actually within that star. And then there's some questions that you'll be answering at the end of it.